Well, there are many different ways to approximate a definite integral, and actually in Calc 1 we looked at some of those ways with the rectangles using the right endpoints or the left endpoints. Well, Professor Berger introduced the trapezoid rule. Instead of using the area of a rectangle, we use the area of a trapezoid. And today we're going to look at Simpson's rule, which is actually based on the area of a parabola. Now, you've probably never seen the formula for the area of a parabola, but there is one. This is it. We take 1/3 of. Now, with the parabola, we split up our interval. It's not just from A to B. It's from, well, A and then in the middle, halfway between the endpoints, we would say it's x sub 2. So x sub 1 is where we start, x sub 3 is where we end, and then x sub 2 is halfway in between. So with the area of a parabola, we have to have an even number of partitions as we get into Simpson's rule. So we can say from x sub 1 to x sub 2 will be the first part, and then x sub 2 to x sub 3 would be the second part. Where trapezoid, we can use any number of partitions there. But Simpson's rule, because of the way the formula for the parabola is set up, we'll have to have an even number of partitions, which we almost always choose that anyway, so that's not that big of a deal. But the formula is basically 1/3 and then the right endpoint of our interval minus the left endpoint divided by 2, and then your function value, f of x sub 1, plus 4 times f of x sub 2 plus f of x sub 3. So again, you probably never have seen that formula before, but it is a valid formula for area. Once we find the integral, how to integrate, it's easier to take the integral of this and go through that rather than doing this formula. But let's go ahead and look at using this formula for a particular parabola. We'll look at the parabola x squared plus 2x, and we'll go from 1 to 4. Okay. Now, thinking about that, this would be the x sub 1, this would be the x sub 3, so x sub 2, halfway in between, would be what?
Between 1 and 4?
Yeah. Okay, it'd be 2.5. Okay. 5/2 might be a little easier. 2.5, however you want to represent that, but a way you could do that, 1 plus 4, and then divide by 2, so 5/2. The average, the mean of the endpoints. Now the area, based on our formula, is 1/3 times, well, x sub 3 minus x sub 1 all over 2. And then the function value, and here I'll go ahead and put in f of instead of the y sub 1 and y sub 2 and y sub 3. But the formula says we have 1 of the f of 1, but then 4 times f of x sub 2, and then 1 of the f of x sub 3. So calculating those, I may need some help on that middle one. 1/3 times 3/2, that'll make things nice. F of 1 plus 2 would be 3. Then plus 4 times, well, f of 5 halves. 5 halves squared plus 2 times 5 halves. I can do the second part. 2 times 5 halves is 5. So 5 halves squared, 25 fourths plus 5. And eventually I'll let you just plug all this into your calculator anyway. So, and then f of 4, 16 plus 8 would be 24. Okay, so let's go ahead. Actually, with this being times 4, that makes this a lot nicer. This part just becomes 25 plus 20. So 45 and 27, 72. And then here we'll have just 1/2 times 72, 36. The area under this parabola from 1 to 4 would be 36. Now, just to make sure we got the formula right, what's an easier way, at least now in Calc 2, what's an easier way to find that area? Definite integral from 1 to 4 of x squared plus 2x, antiderivative, actually might fit it all in there. So 4 cubed over 3 plus 4 squared, then minus 1/3 minus 1, and let's see, we'd have 64 over 3 minus 1 over 3 would leave us 62 over 3. No, 63 over 3. 64 minus 1 is, 63, not 62. 63 over 3, which is what? 21. Plus 16 would be 37. Minus 1 is 36. So now you have a couple different ways to do that. Well, yeah, the definite integral turns out to be easier than the formula, so that's why you've probably never seen the formula. But
is there anything that would throw that one off?
No. This is the formula for the area under a parabola. It just gets very complicated at times, and many times much easier just to do it with a definite integral. But for Simpson's rule, we use this formula, and so really as we look at approximating a definite integral, if we can't find the antiderivative of it, there are functions that don't have antiderivatives, at least don't have antiderivatives we can write out. They exist, we just can't find a formula for them. But if that's the case, we can use the area under a parabola to estimate what that is. Okay. And we'll go ahead and what's called Simpson's rule we can say the definite integral from a to b of f of x dx is approximated by 1/3 times the quantity of b minus a over n times f of x sub 0 plus 4 times f of x sub 1 plus, well, in the idea of the parabola, area under the parabola, this would be plus 1 of f of x sub 2. But then the next three x values, we use the parabola again, so f of x sub 2 would be the starting point for the second parabola. So, like the trapezoid rule, one piece gets used twice as the end of the first parabola and as the first part of the second parabola. So then the middle of the second parabola is going to be 4 times the x sub 3 plus, well, x sub 4 represents the position of the last part of the second parabola, and then again the first part of the third parabola. So it gets used twice as well. And on and on and on until we get to the very last parabola, closing in on B here. Well, we kind of have to think the one previous to B, the one previous to x sub n, would be 4 times x sub n minus 1. And then finally, the last one would be just 1 of the x sub n. Because that last parabola only gets used once as the final part of our last parabola. So this is Simpson's rule. And again, it looks very similar to the trapezoid rule, except we're using the parabola formula rather than the trapezoid formula. Questions there? Now, to kind of give you an idea of how to work these problems, or how these approximation techniques compare, I went ahead and did one of these, integrating from 2 to 3 the function 2 over x squared. Now, this one is a value we can find exactly, but I just wanted to show you some of the values of the trapezoid rule, the Simpson's rule, and then also going back to our right-hand rule and left-hand rule with the rectangles. You remember back that far, back in Calc 1. This is exactly equal to 1/3, or the repeating decimal 0.33333. Okay. Now, if we had looked at this back in Calc 1 with using the left endpoints, the approximation, and using 4, all of these approximations will use n equal 4. So the left endpoints would have come up 0.36988 that's probably 6 decimal places. That's probably good enough. Turning it around and using the right endpoints, we would have gotten 0.300437, which those aren't too bad, but rectangles and only four rectangles, that's not going to be extremely accurate. Now the trapezoidal rule, this one comes out to be 0.335159. So a little bit closer And then using Simpson's rule, .333360. So we're almost to 4 decimal place accuracy. Almost, not quite. It'd round up to 4, where the exact answer would be .3333. We'd be off by a little less than 1/10,000th. That's pretty accurate. Where these others, I mean, these two are around to the nearest tenth. Not good. But of course we're only using n equal 4 over one entire unit. N equal 4 isn't going to get you a lot of accuracy, although it does with Simpson's rule. So definitely Simpson's rule is more accurate than these other approximations. And if you ever go beyond this calculus series, get into some higher level mathematics, you may run into some other estimation techniques that can calculate integrals even more accurately. But at this point, Simpson's rule is probably the best approximation technique for us. So with that, problems on 4.6, our homework assignment, we'll ask for both trapezoid rule and Simpson's rule. And then you can kind of, some of them actually want you to find the exact value and then compare, see how close your approximation is. Some of them just say find the approximation value using those two. So have at it.